Hey everyone, and welcome back. Before we begin here today, please make sure that you like and subscribe because it really does help out our channel and it also helps us reach others in need of assistance with these topics. So in today's video, we're going to be covering differential equations and we're going to be looking at exact first order equations, and this will be our third part in this particular series. So we are tasked with solving this differential equation shown on the screen, given the boundary condition of y of 2 is equal to e. So what we're looking for here in the end is what y equation makes this true. So if we didn't know that this was an exact first order equation, so don't look at the title. If we didn't know it, this would be the process to confirm that this is an exact first order differential equation, and the preceding procedure will show you how to solve it. First, let's check to make sure that this is an exact first order. So what we're going to do is we're going to rearrange, excuse me, we are going to rearrange in the form of mx or mdx plus ndy is equal to 0. So we're going to have a bunch of terms attached to a dx and then terms attached to a dy. So what we're going to do is just rearrange these. So take dx to the left side, and then the remaining portion take to the left side as well. So when we do this procedure, we end up with the natural log of y dx plus x over y dy is equal to 0. So what this means that this would be my m and this would be my n. Now, looking at this equation as written, we cannot use the separation of variables method in order to solve. So we're going to have to check and see if it is an exact first order. And if it is an exact first order, the following would be true. If we would have the partial derivative of m with respect to y must be equal to the partial derivative of n with respect to x. If that is true, then this is really an exact first order differential equation. So let's go ahead and let's start finding these. So if we have the partial derivative of m with respect to y, which would be the partial derivative with respect to y of the natural log of y, which is just saying it's the regular derivative of it, which is just 1 over y. So then we would have the partial derivative of n with respect to x, which is equal to the partial derivative with respect to x of x over y. Now, since there is a y in here, we'll have to treat that as a constant and then basically just take the derivative of x. And when we do so, we end up with 1 over y. So this holds true that the partial derivative of m with respect to y is equal to the partial derivative of n with respect to x. So we do have an exact first order differential equation. So this would be the procedure in order to solve an exact first order differential equation. So what I'm going to do is I'm going to set my beginning expression here of mx or mdx plus ndy equal to 0. I'm going to set that equal to dg in order to find what my y equation is. Now, looking at what I have here, if I set this equal to dg, the following is also true. If I take the partial derivative of my g equation, which is now this, with respect to x, it ends up being equal to m. And if I take the partial derivative of my g equation with respect to y, it ends up being n. This will come in handy here a little bit later, but let's work on the left one here. Let's work on the partial derivative of g with respect to x is equal to m. So what this means here, if I scroll down just a bit, what this means is that I would have g is equal to the integration of m dx plus h of y. Now, this h of y is just a constant equation. Because I'm taking the derivative with respect to x, I could have a constant value here in terms of y. So I have to include it. Just like when you integrate any type of form, you're going to end up with a constant. But since we're taking with respect to x here, we could have some kind of y equation occurring here, or an equation in terms of y. So we have to include it. So this would just be the integration of m, which is the natural log of y, dx plus hy. So integrating this, we end up with g is equal to x natural log of y. If we take the natural log of y as a constant, because we're integrating with respect to x, plus h of y. Now, we have to determine what this h of y equation actually is, or if it is just a number, or if it is just some kind of y. So what we're going to do is that we're going to take the partial derivative of g now with respect to y, treating x as a constant. So basically like the reverse of what we just did. So, well, not exactly the reverse, but you get the idea. We were working with x, now we're going to be working with y. So partial derivative of g with respect to y, this would be equal to the partial derivative with respect to y of x natural log of y plus h of y. So treating x as a constant here, we would just end up with x over, since the natural log of y is 1 over y, and then plus the partial derivative of h with respect to y. Okay, so how do we solve for this portion right here? Well, look what we have up here. The partial derivative of g with respect to y has to be equal to n. Well, we also have the partial derivative of g with respect to y is equal to this right here. So what we're going to do is set these two equal to one another. Well, if you remember what n is just x over y. So if we set these two equal together, what we're going to have is our partial derivative of g with respect to y is equal to n, which is just x over y. So for this statement to be true, what this means here is that this must be 0. So the partial derivative of h with respect to y has to be equal to 0. So that means it doesn't contain any y in it. It has to be a constant value. So what that means is that if you just take h and you integrate it here with respect to y, we would just end up with a constant value, because if you integrate 0, you just end up with a number. So what that means is that this h of y doesn't contain any kind of y variable in it. It is just a single number. So let's rewrite g here with this new information. So we end up with g is equal to x natural log of y plus a constant. Well, do you remember what dg is equal to? Well, dg is equal to 0 here. So just like when you take the partial derivative of h with respect to y has to be equal to 0, dg has to be equal to 0 as well. So what that means is that, well, same thing here, that is equal to a constant as well. So what we can do is that we combine these two constants together into a single constant. So our equation ends up being c is equal to x natural log of y. Alrighty. So now we have a single equation here in terms of y and x and a constant. Now, if we weren't given the boundary condition, this would be our answer here. But we are given a boundary condition of y of 2 is equal to e. So what this means here is that y is equal to e when x is equal to 2. So go ahead and plug these in here and determine what this constant needs to be. So this would be c is equal to 2 natural log of e. Well, natural log of e is just 1. So this means that c is just equal to 2. So let's go ahead and plug this in here. So we would have 2 is equal to x natural log of y. Now, we are looking for the y equation. So we're going to have to rearrange this in terms of y equals. So divide by x on each side. So we have 2 over x is equal to the natural log of y. And how do we get rid of the natural log of y? Well, we're going to have to take e on each side here. So it'd be e to 2 over x is equal to e natural log of y, which that just drops out. And then we're left with what's in our natural log here. So my y equation ends up being e to the power of 2 over x. Now, that would be my final answer for what y equation makes the original differential equation true. Now, what you can do if you have the time is double check to make sure that this y equation is correct. And how do we do that? Well, we're just going to plug it back into our original differential equation expression that was given. And the original expression was the natural log of y is equal to minus x over y dy dx. So we're just going to plug in our y terms here and make sure that this expression is true. So we're going to work on this one first, the dy dx. So basically what we're going to have here is the derivative with respect to x of e 2 over x, since that's my y equation. Now, I'm going to have to utilize the chain rule here in order to solve this. So I'm going to set a u variable equal to 2 over x, and then my f variable is equal to e to u. So that means that dy dx would actually be equal to df du multiplied by du dx. So I would take the derivative with respect to u of my f, which is just e to the u, and then I'm going to multiply that by the derivative with respect to x of my u equation, which is just 2 over x, which this is essentially, if I rewrite this, 2x to the minus 1. Pretty simple expressions here. Since the derivative with respect to u of e to the u is just e to the u, and then the derivative with respect to x of 2 times x minus 1 pops out to be minus 2x to the minus 2. So let's plug back in our 2 over x for our u variable here. And then my dy dx actually pops out to be minus 2 over x squared multiplied by e to the power of 2 over x. All right, so that's what I'm going to plug in right here. So let's drop this entire expression down and plug in our y equations here. So we would have the natural log of e to the power of 2 over x is equal to minus x over e to the power of 2 over x multiplied by minus 2 over x squared e to the power of 2x. So a lot of stuff cancels here because this just turns into be 2 over x on the left side here because the natural log of e. And then looking at what we have here, well, we have e to the power of 2x divided by e to the power of 2x just becomes 1. The minus signs will cancel and become plus. This x will disappear, and then we're just left with 2 over x here. So we have 2 over x on the left side, and we are left with 2 over x on the right side. So that means that my check worked out, the expression holds true, and this y equation right here is my final answer for the starting differential equation expression. And that's how you would solve that particular problem. So I hope this video was helpful, and if you want to see more problem solve this Friday, please check out the other videos on our channel. Also, if you haven't done so already, please like this video, leave a positive comment below, and subscribe to the channel. Thank you for watching, and I hope you have a fantastic day.